Alright, my name is Tom Hegmeyer. I'm finishing up my Instructor 2 project with series pumping procedure. We have our mutual aid department, Brentwood, here, who we're going to work with on a real fire in a high-rise. So they're here. We're going to go over just the critical factors in setting up this operation, and then we're going to go out and do a training, put it into service. So in a relay pumping or series pumping operation, we need to set that up for high-rise buildings because it's a high-pressure operation, and so these are kind of the critical factors in deciding how we set that up, why we set that up, and when we set that up. So these buildings operate under system demand pressure. So what that is the pressure that all the sprinklers and all the PRVs and standpipes are designed to operate with. So of course it's going to depend on the height of the building, but that is based on providing 500 gallons per minute at the two most remote outlets. So that's based on that. So what they do is they go to the roof, open up the valves, and the system demand pressure, is engineered to supply at least 500 gallons a minute from the two most remote valves on the most distant standpipe on the roof. So, and each additional riser would add 250 to this. So if you have two risers, it's going to be a 750 gallon per minute system capacity. If you have three, it could be 1,000. And then when we arrive on scene, if we don't know that right off the top of our head through pre-planning, which it can be obtained in pre-planning through the sprinkler test records, and it'll be listed as churn pressure. So once they test that, it'll be churn pressure. So no water's flowing through the building. The pressure that pump creates is what the system is designed around. So that's what we need to meet or exceed to provide water to that building appropriately. So our estimation here gets us very close. I've checked them with a lot of our reports. You would take 100 psi plus 5 or 6 times the number of floors minus the first floor, and that would get you very close. So the example over here we're going to use would be for one of our buildings. It's 265. So we'll get back to that later. But and then the FDC. A few things about the FDC are there were some questions of, well, what if we break one, or what if we overpump one? Is it dangerous, or what do we pump it at? So the FDC is rated and tested to at least 200 psi for all systems, or 50 psi above that system demand pressure. So it's 265, it would be 50 above this. So that's our buffer zone of what we can safely pump into the building. So how we do that will be a command decision or set up through our SOPs or SOGs, which is up to operations and how we're going to do that. But we're at least going to set the operation dry and be ready to supply backup water to the fire pump in the building, right? So that, or we can start pressurizing that FDC at 50 psi below the system demand pressure, which would allow for seamless, uninterrupted water if there was a pump failure in the building. And if it's determined by command that, well, this is a sprinkler building, but we're still seeing fire growth or signs of fire up on the floor, it may be determined that we want to take the building over.
Explain to them, they may not know that we're going to rely on the pump in their system before we do that.
And so we're going to rely on the building pump to work until it doesn't. And so that's why, in order of operations, this could be possible interruption if that pump were to go out. This would be uninterrupted, maybe a pressure drop, and then this would be we're in control. So the way these systems work is you're either providing the system or you're pumping into a closed check valve. So the way the FDC is piped in is it goes into the discharge system that's providing the building. And the only thing between the water discharge supply in the system and the pumper is one check valve. You can't close it off, it can't be, shut off. You're only pumping into a check valve. So you're either pumping in or that pump is pumping back against the check valve. So that's another important thing to realize. Is there any questions about that?
So you're never able to assist a fire pump. It's either the fire pump's going or you're taking over.
Right.
One or the other.
Right, and then, hydraulically, real life, if you're pumping within close, the same pressure, it could go back and forth a little bit, depending on as the demand changed inside the building. Whichever one was providing more pressure at that time, based on, we know the relationship between residual and discharge pressure, right? So it could, in theory, go back and forth, but any one time, you're not going to be both feeding the system, and you may not want that anyways. But the other factor is equipment limitations. So our hose, 5-inch hose, is, any hose, we're only supposed to use up to 10% below the service test pressure. So you guys have had really good hydrants. We've been limited in training of using 5-inch because how good the hydrants are. Like being a pump, most 5 inches is tested up to 200 psi, so 180, 185 is the top that we should use. So depending on 2.5 or 3-inch hose, it just depends, but not to exceed that. So this could be a limiting factor, and most times when we're going to go up pressures that are higher, we're going to be using 2.5 or 3-inch hose, right? And then intake relief valves. We'll get into this again, but if I tell you to give me something above that intake relief valve, it's going to shoot off, and then we might be wasting our time there. So knowing what these pressures are set at and making sure they're set at the correct level is another important factor. And then net pump discharge pressure. So what this is the pressure that the pump's creating. So if we're on a hydrant, we have 50 coming in. If we're at idle, usually our pumps create 50. Then we have 100 coming out automatically at idle. So the way these pumps are designed is that once we exceed the difference between intake and discharge, our static tank, which would be 0, and discharge at 150. Once we exceed 150, we're actually going to decrease the capacity of our pump to discharge water. So NFPA states it, and it's the way these apparatus are designed. We want to keep the difference between what we have coming in and coming out at 150. Really in all operations. It's okay to exceed it, if you don't need that much water, but if you're thinking about maximizing any water you're sending out, you want to keep the difference at 150 or below. So that just says, that's what it says here. It's what we create. It's the discharge PSI minus the intake PSI. For relay or series pumping, they recommend having one pumper for every 150 psi of that system demand pressure. So once I've seen and read, that can be interpreted a couple ways, but once you get above 200 psi, it might be a good idea to add an extra pumper. One for redundancy and 2 for balancing the work between pumpers. And to split the load, balancing the work. So there will be at least one supply pumper and an FTC pumper, and how we split the load is this equation right here. So you figure out what your system demand pressure is. So if that's 265, you subtract your hydrant pressure, and we know that that is 80 psi, and then you take that left over and divide it by 2, and that's the net pump discharge pressure for each engine. So if you see that 80 psi is coming in 2514. What we say? They're going to discharge 125 because that's our intake relief valve, and then we have that coming in. We're going to create the rest, which will be 140, which will be within our goal of 150, right? And then we'll discharge 265 psi. So it's math and equations. You might have to look at it a couple times, but we know our goal, and now we know why we want to set up the series pumping is to keep our net pump discharge pressure below 150 where we can maximize the capacity of our pumps, okay? Because if we just try to create all the pressure with one truck, you may only be able to be as good as the system or less. You know, you may be calling for more demand inside a system than you can provide if you use one. And so once we get all this set up, you know, get the trucks in line, this is what our training is going to look like. We're going to set up a series pumping procedure. So 2514, well 3214 will arrive on scene first. We're going to hook up dry to 3212 on each side, which will act as an FDC. And then we're going to estimate that our system demand pressure is 265. So Brentwood arrives on scene. They're going to, you know, do the high-rise thing, drop off their guys, take the equipment up, and then I'd probably communicate with, or whoever's driving might communicate to help establish a water supply. And, you know, that could be done a number of ways, but in this drill, we're going to tell you to lay from us to the hydrant and supply us with 125. You know, so if I get there first, we set up our dry lines, we'll figure out our system demand pressure. We can at least figure out, well, if I have 115 coming in, that I can maximize my pump. So you give me anywhere between 100 and 125. To keep it simple. If I tell you to do some math in your head, that ain't gonna work. You know, say 2514, lay from me to the hydrant and then send me 100 or send me 125. So going through all this, we're still within the limiting factors of our LDH here, and then, you know, well within our limiting factors of the 2.5 there. So, and once we get all that set up, assuming we're pumping at or below the system demand pressure, right? So we're just pumping in that check valve or a backup. You know, there's, again, the benefits there are, one, we're going to be pumping in that check valve, but we're going to be able to provide seamless, uninterrupted water to interior crews if something bad happens. So when we're doing that, just like any other procedure, we need to keep our pumps cool. So each truck, we should make sure they're pumping at least 100 gallons per minute, however they want to do that. Crack and overfill your tank fill, or you can get a booster line secured somewhere else or in a remote area and flow your booster line. That makes sense. And then verifying flow. You guys have flow meters on your truck, right?
Yeah.
On certain ones.
Oh, yeah, just
Certain
certain
ones?
discharges.
Yeah.
Do you have it on your LDH?
I don't think we do.
No.
I was figuring probably not, but there's benefit there. So sometimes you're pumping in that check valve. It's really important to know, like, if the demand inside the building has rise to the occasion where you've overtaken the pump, that can sometimes happen without you knowing. So one way to tell is if you have flow meters on those discharges or gate down those discharges gradually. And you may see it with one. If you have 2 charged, you may have to do the second one. And if you see your residual go up and your discharge stay the same, then you know I've been providing system because my residual pressure has changed, fluctuated just a little bit, right? So if there's no change at all, then everything is static and you're pumping into the check valve. So that makes sense. So if we're providing near the system capacity inside, or the system capacity inside has outrun their water, they don't have the ability inside the building to keep up with demand. So if we get above 500 or 750, which would be 2 or 3 hose lines going in a building, then we're going to see that change in residual pressure as we gate down. So that's it. That's the critical factors for kind of why we'd set it up how we would, and this is how we're going to do it. So 3214 would arrive on scene first, and we're going to call for water based on those equations or the system demand pressure. But that's, a couple of these simple equations are how we determine what we need to give the building and then how we're going to do it. Yeah, Vern, did you have a question?
You talk about RPM mode?
Thank you, I meant to write that up here. So, anytime modern attack pumpers have pressure governors on them for attack mode. So changes in residual pressure and discharge pressure will remain constant on our lines using that governor. So that works by understanding the relationship between residual pressure and what we want to come out. So as lines anywhere, if we're just fighting a house fire or in a building, as like we said, if you're opening and closing discharges, the demand goes up and down. So the residual pressure goes back and down. So it goes up and down. So as that feedback through pressure is communicated from truck to truck, if the supplying pumper stays in PSI mode, then those pressure governors will fight each other. They'll kind of go all over the place, and they call it RPM hunting. So anytime you're feeding another truck or a ladder truck or a pumper on scene, it's good to get your pressure where you need it and then just click over to RPM mode. That way you it sets a certain RPM and you're going to provide constant flow based on that. So if you really need more water, if I'm calling for more water, or you're really trying to maximize flow from a ladder truck, you can pump it up at that point and bring down your residual pressure, provide more out if you need it. But then, just good communication needs to be had anytime you're flowing big water, right? So, yeah, thanks, Vern. That was another key point I wanted to bring up. So, when you're supplying another pumper anytime in the field, you should go into RPM mode once you get set up.
And that means you need to also monitor that a lot closer than in pressure mode.
Right. Yeah, so your truck's not going to rev up and down based on need. It's going to, basically, the residual will drop and the discharge pressure will drop depending on the demand that's requested from the attack pumper. So. Any other questions? All right, we'll go out and we'll get 3212 and 3214 position, and then we'll need 2514 to hook up on the hydrant and feed 14. So maybe 12 we'll figure that out. We can shut the camera off.
12.
Shut the camera.